Assalamualaikum warahmatullahi wabarakatuh to dear panels. My name is ZAHIRAH binti MOHAMAD and I am from class RCF AP 2207C. So today I would like to present my final year project entitled Coastal Inundation Prediction along the east coast of Peninsular Malaysia using multi-decadal satellite altimetry data. Coastal inundation or coastal flooding are caused by a combination of natural and man-made sources such as heavy rainfall and climate change. But the main contribution for coastal flooding is due to the sea level rise. This study focused on predicting coastal inundation along the east coast of Peninsular Malaysia by analyzing long-term satellite altimetry data. The main objectives are to estimate the rate and magnitude of sea level rise and assess inundation risk using open-source digital elevation models (DEMs). The Radar Altimetry Database System (RADS) software was used to extract and process the satellite altimetry data. Robust regression method was applied to determine the rate of sea level change, and the results were validated with tide gauge measurements. Future sea levels were projected for the year 2100 and inundation analysis was performed using 3 DEMs, Lost World 3D, SRTM, and NASA DEM using ArcGIS software. The results showed varying rates of sea level rise across different states, with Kelantan experiencing the highest rate. Inundation simulations showed significant differences depending on the DEM used. These findings highlight the critical role of high-quality elevation data and long-term satellite records in coastal flood prediction and planning. Now I move on to the problem statement. Tide gauges are commonly used to monitor the sea levels, but the coverage is limited to fixed coastal location and lack the ability to represent regional variations in sea level rise. This makes it difficult to estimate absolute sea levels, especially in areas far from tide gauge stations. Satellite altimetry addresses this limitation by offering broader coverage and higher spatial resolution, enabling improved estimation of sea level changes along the coastlines. When validated against the tide gauge data, satellite altimetry has shown high accuracy, making it a reliable tool for sea level monitoring. The accuracy of digital elevation models (DEMs) plays a key role in determining inundation zones as land elevation influences flood risk. Although high-resolution DEMs such as LiDAR offers precise elevation data, they are often costly and less accessible. Open-source DEMs provide a more accessible alternative but generally have different accuracy, which may affect the reliability of coastal inundation prediction assessments.
So there are two objectives of my study. First is to estimate the rate of sea level rise for coastal inundation prediction year 2100 using satellite altimetry data, and second is to evaluate the accuracy of open source DEM model for coastal inundation predictions.
So this is my methodology, which starts with literature review. In my study, there are two types of data used, which is the sea level data and the elevation data. The sea level data consists of satellite altimetry data, which is my main data, and tide gauge data. The satellite altimetry data were extracted using satellite altimetry database system software, where then process it with the output of sea level anomaly, then be used to calculate the sea level rise. The tide gauge data were acquired in the Permanent Service for Mean Sea Level, or PSMSL for short, which is an open source data. Then the data were cleaned and rearranged before use to calculate the sea level rise. The calculated sea level rise data using the tide gauge will be used to validate the satellite altimetry data before calculating the sea level rise prediction for the year 2100. For the elevation data, it consists of GNSS data which were acquired from the existing survey and global DEM data which were obtained from open source data. After the DEM data being processed, the GNSS data were used to validate the DEM data. Then the DMs were used for the simulation of the coastal inundation prediction based on the satellite altimetry data calculated for the year 2100.
Now we move on to the result. The line graph shows the rate of sea level rise along the east coast of Peninsular Malaysia on the year 2100, covering three states, which are Kelantan, Terengganu, and Pahang, where the x-axis represents the latitude and y-axis represents the rate of sea level rise in millimeter per year. In Kelantan, the rate of sea level rise varies between 4.1 mm to 5.1 mm per year, indicating localized acceleration in the sea level increase. This suggests that the northern region is expected to experience the highest rates of sea level rise than the other regions. As we move southward, Terengganu shows a more variable trend starting at around 5.0 mm per year in the north. Then, a noticeable dip below 3.6 mm per year is observed around the mid-latitudes of Terengganu, indicating a relatively slower rise in this section of the coast. There are minor variations suggesting certain areas may be slightly less vulnerable, although the overall trend still indicates the risk of coastal inundation. Then we move on to Pahang. The rate continues to decline gradually, falling below 4.0 mm per year in most areas and reaching the lowest values of around 3.0 mm per year towards the southern end of the state. This trend suggests that southern regions may face relatively lower, but still significant, sea level rise compared to the northern coast. Overall, the graph shows a clear spatial variation in sea level rise along the east coast, with Kelantan being the most affected, followed by Terengganu and then Pahang. These insights are crucial for prioritizing coastal protection and planning efforts based on regional vulnerability.
So these images represent the comparison visual analysis of three different digital elevation model (DM) datasets used in this study, which are SRTM, NASA DM, and ALOS World 3D, which all have 30 meters resolution and used for the coastal inundation mapping in Kelantan, Terengganu, and Pahang. Then, the table here shows the percentages of the inundated area for the year 2100, where NASA DM consistently shows the highest predicted inundation in all states. ALOS World 3D shows the lowest predicted inundation, indicating higher terrain or more accurate elevation representation. And finally, SRTM, where the results fall in between, but closer to NASA DM for Kelantan and closer to ALOS World 3D for Pahang and Terengganu. So this is the findings of my study. The study shows that the predicted rate of sea level rise by the year 2100 varies across the east coast of Peninsular Malaysia, with Kelantan showing the highest rate at 4.63 mm per year, followed by Terengganu at 4.33 mm per year and Pahang at 3.89 mm per year. The estimate average sea level height relative to the EGM 96 were 1.7 meters for Kelantan, 1.837 meters for Terengganu, and 1.727 for Pahang. Inundation projections using 3 different DMs revealed significant differences in predicted flood extents. So these are the novelty of my study. First is the use of multi-decadal satellite telemetry data. So in my study, I use over 30 years of satellite telemetry data, which is from year 1993 to 2024, to estimate sea level trends, which providing a long-term perspective rarely applied in local coastal studies. Next is state-level sea level rise prediction for the year 2100. So this offers specific predictions of sea level rise rates and projected heights for individual states, which is Kelantan, Terengganu, and Pahang, which enhances regional planning. Next is comparison multiple open source DEM. My study evaluates and compares the inundation results using 3 different open source DEMs, which is NASA DEM, SRTM, and ALOS Work 3D, which highlighting their impact on flood extent estimation. Next is validation with tide gauge data. This strengthens the accuracy of satellite-based sea level trends by validating the results with ground-based tide gauge measurement. Next is the inundation mapping based on projected sea level for 2100. My study provides visual and quantitative flood risk predictions using satellite-derived projections rather than relying solely on historical or present-day water levels. Lastly is application to Malaysian East Coast context. This addresses a geographic region that is underrepresented in global sea level rise modeling studies, offering novel insights into local coastal vulnerability. As the conclusion, this study reveals a significant risk of coastal inundation along the east coast of Peninsular Malaysia by the year 2100, especially in Kelantan and Terengganu. Satellite telemetry data combined with open source DMs provide valuable insights into long-term sea level rise and inundation risks. The variation in inundation areas among DEM sources highlight the importance of DEM selections in coastal studies. Future work should be integrate socio-economic and infrastructure data for more effective coastal risk planning. That's all from me. Thank you.